Right, we're going to go over review for exam one. In the first question, we're going to look at homogeneous mixture versus heterogeneous mixture. Keep in mind that sometimes these items do not belong to a category in a question. Just pick the ones that fit into the correct category. So sometimes you use all of it, sometimes you don't use all of it. In this case, garlic salt is going to be categorized as homogeneous mixture because you expect garlic salt to be the same distribution the whole entire sample. Gold-plated ring will be heterogeneous mixture because it's not the same throughout the whole sample. You're going to have the outside as gold, inside as not gold. Distilled water and ice cubes are not mixtures. They're pure stuff. So it doesn't fall into either category. And then red ink is going to be a homogeneous mixture. The next question, physical versus chemical change. Let's look at this one here. Formation of icicles in cold weather. So basically it's just ice forming, right? So that's a phase change, and phase change would count as physical change. So this one's physical. All right, formation of soap scum. So formation of soap scum is when the soap particles, it reacts with maybe part of the water that's hard, that has ions in it, and it makes a soap scum. So that essentially is a chemical change. If you mix baking soda and vinegar, you can create a chemical reaction that forms bubbles, which is gas, and it just forms bubbles. And that's what we use for the volcano demonstration. So simply mixing baking soda and vinegar is going to be a chemical reaction. If you activate a glow stick, you're going to be doing a chemical reaction as well. If you dissolve sugar in water, the process of dissolution, just taking something and dissolving it in water, is not considered a chemical reaction. This one is physical. All right, the next question. A student weighed this amount, 560.97, and this unit here is called micrograms of sulfur in the lab. This is the same mass as how many kilograms in the lab. Please report your answer in scientific notation. So when we want to type in scientific notation, example will be 1.23, use the star, and then 10, and then the symbol for up, and then -1 or +1, whatever the power is going to be. And you want to make sure to also use the correct sig fix. So how are we going to do this question? You need to know how to convert from microgram to kilograms, okay? So keep in mind, when you're doing micrograms, you have to remember micro is the smaller unit. And I know that 1 gram is the same as 1 times 10 to the power 6 of micrograms, correct? So that's one conversion that I can remember. Or you can also say 1 microgram is 1 times 10 to the minus 6 grams. I'll write that down too. It really is the same thing, but I prefer to use the ones without the negative signs, but it's just a matter of preference. They both will give you the same answer. Now, the next conversion that you need to know is 1 kilogram contains 1,000 grams. So that one's a pretty common one. And if you really wanted to, you can write it the other way. You can say 1 gram is 1 times 10 to the minus 3 kilograms. But I'm going to choose the conversions without the negative signs here for this question. Okay? Now, when I know these are the same thing, whether I write 1 gram over 1 times 10 to the power 6 microgram, or I write 1 times 10 to the power 6 microgram divided by 1 gram, because they're the same thing, it doesn't matter which one you put on top or bottom. Same idea here, 1 kilogram is always equal to 1,000 grams. Top or bottom doesn't matter. I can put kilograms on the top, or I can put kilograms on the bottom, depending on the equation. So the trick with converting is you always want to write down the number you start with. So I'm going to start from 560.97 micrograms, okay? And then I'm going to try to convert it Number one, from micrograms to grams, and then from grams to kilograms. So I have to do a two-step conversion. If I want to change it to grams, I'm going to put the grams that I want on the top and the micrograms that I want to cancel off on the bottom. So that's how we're going to decide who you multiply or divide with. And in this case, you'll multiply with 1 gram and divide by 1 times 10 to the power 6 micrograms. That way we convert off the microgram. Our answer is in gram now. And then the next step, we want to convert to kilograms. So I'm going to put kilograms on the top, grams on the bottom. 1 kilogram is to 1,000 grams. So that way I can cancel out my grams and my answer will be in kilograms. So when you put this together, you'll get 5.6097 times 10 to the negative 7 kilograms. Now, if you were to type this out on your computer, you would simply type 5.6097, and then you put that star sign, and then 10, and then you type the up sign, and then you write negative 7. Okay, that is number 3. So I'm going to show you these items here. There's 3 green marbles. So that's going to be one of your Easter eggs to look for. 3 green marbles. All right, let's go to the next question. The next question we have is, what is 497.92 Kelvin in Celsius? Please use the correct decimal places in your answer according to the significant and put your answer with the correct SIGFIG rules. Report only the numerical value without typing in the unit. So all I want is just a number when I write it here. I can do my math down here. So how do we convert from Kelvin to Celsius? And you can actually refer to the chart that will be provided on your exam if you forgot. But over here, you can see that we have 0 Celsius is the same as 273.15 Kelvin. So that's going to be a good number to remember, 273.15 Kelvin. So in this case here, if I have 497.92 Kelvin, I will want to subtract 273.15 to get it to go to Celsius. So my answer would be 224.77. And usually when you do conversion and temperatures, we keep the original decimal places because we know we're going to add or subtract. And I like to keep this same decimal place. So in this case, your answer, when you write it in, you just put 224.77. And this will be in Celsius. All right, let's do the next question. If the percent yield for the following reaction is 76.29%, how many grams of KClO3 are needed to produce 15.78 grams of O2? Please express your numerical answer without units. Use the correct SIGFIGs and do not use scientific notation here. So all we're looking for is just a plain number without units and all that. So how do we do this calculation here? So they're saying there's a percent yield, 76.29%, and then they are asking you, how much of my reactant do I need to produce this much amount, 15.78 grams of my product? So if you think about it, if I use this reaction here, I need to use the 100% number. So they're saying 15.78 grams is going to be only 76.29% because the reaction is not perfect. It's not 100% yield. There's only 76.29% yield. So you should first take 15.78 grams of O2, and then you want to use the fact that you know this 15.78 grams is going to be just 76%-ish, get it to 100%. Once you have the 100% number, then you take this and you work backwards from 3 moles of oxygen to 2 moles of KClO3. They gave you the molar masses here, so we'll try to use that. So what I would do is, number one, I know that 15.78 grams of O2 is 76.29%. So I'm going to try to use that knowledge here. I'm going to get it to 100%. So I'm going to do 100% is what I want. And I know I have 76.29%. And that number is the same as 15.78 grams of oxygen gas. So that will get me the real number that I want to use for calculation for the mole-to-mole ratio. So once I get the grams of O2, that's 100%, I'm going to have to convert it to moles of O2 first so I can get to mole-to-mole ratio. To get to moles, that means I have grams. I want to cancel out the grams of O2 and want to get to moles of O2. So that means I'll put 1 mole is 32.00 grams. So then I cancel off. And now I have my answer in moles of oxygen. Now in this case, we know that the ratio of oxygen to KClO3 is 3 moles O2, right there, to 2 moles of KClO3. And then I'm going to go ahead and convert it to grams. So 1 mole of KClO3 is going to weigh 122.55 grams. KClO3. Running out of space there, but if you put this in your calculator, we're going to cancel off the moles of O2, get moles of KClO3, cancel that off, you get grams of KClO3 is your answer. So the answer here, if you put it in your calculator and you end up keeping how many sig figs? 4. These numbers are unlimited, so you just ignore. This one has 5, this one has 4, this one has 4. We're going to keep 4 sig figs. 100% here is also exactly 100. It's unlimited sig figs. So my answer should have 4 sig figs. And I'm going to keep 52.81 grams of KClO3. Now, because it said don't put units in, you would just type in 52.81. Okay, so that was number 5. Now let's take a look at number 6. If the percent yield for the following reaction is 79.54%, so again, they mentioned it's not 100%, and you use 59.31 grams of the reactant. Nitrogen dioxide is the reactant here. So this question is a little backwards from the question we just had. If you take a different look at compare these two questions, this one says percent yield is not 100%, and how much reactant do I need to make a certain amount of product? And that's how we would do it up here. And this question actually is the opposite. It says, if my percent yield is this certain number, and I use this much reactant, how many grams of the product, in this case nitric acid, am I going to make? So it's kind of the same concept, but a little different, okay? So to do this question, we are going to, again, need to know that this here is going to be all of the reactants we have. But when you make the calculation here using this reaction, it's going to get you to the theoretical yield, which is the 100% mark. Once you get the 100% mark, they said, how much do you actually make? Because it's not 100% efficiency, it's only 79.54%. So once you get your answer for nitric acid grams, you actually take 79.54% of that number to get the final answer down here. Okay, so what we want to do is start with the fact that you know you have 59.31 grams of your reactant. So I'll write that down, 59.31 grams of NO2. And then what I'm going to do is I am going to convert to moles. Always convert to moles because you can't compare in grams. So we have to turn it to moles, and then we do the mole-to-mole ratio. So it's always grams to moles, mole-to-moles ratio, and then back to grams. So in this case, 59.31 grams NO2, and then 1 mole of NO2 weighs 46.01 grams of NO2. So we cancel out grams of NO2, you got moles of NO2, and then we'll do the mole-to-mole ratio. We have 3 moles of NO2 to make 2 moles of nitric acid. Now, why did I put nitric acid on top? Because I'm trying to change away from moles of NO2, and I want to get it to moles of nitric acid. And then after that, I want to turn it to grams of nitric acid. So grams will go on top, moles will cancel off by going on the bottom. You multiply with the stuff on top, you divide with the numbers on the bottom. So in this case, 1 mole of nitric acid is going to weigh 63.01 grams right there. Okay, so I would cancel my moles, get my answer in grams. Now remember, this is the 100% mark, right? So this is my 100% mark. I'm going to get this answer and then say, okay, I know this one is 100% because this is my theoretical. But they're not asking for that. They want the 79.54%. So when you put 59.31 divided by 46.01 times 2 divided by 3 times 63.1, that should give you the answer for 100%, which is like, I'm gonna write down extra numbers. But we'll stop at the 4th sig fig. Again, 4 sig figs, 4 sig figs, unlimited, 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 4 sig figs, unlimited. So we keep 4 sig figs. I write 5 numbers, underline the 4th one, so I know it really stops there. Then we'll take 79% of it. So 79.54%. And then I know 100% is the same as 54.149 grams. So my answer would be 43.07 grams of HNO3. And in this case here, I'll just put down 43.07. Again, 4 sig figs, 4 sig figs, unlimited. So 4 sig figs in my answer. All right, let's go to number 7. For number 7, this is a chess piece, and this is a knight. Notice this is a clear chess piece that's a knight. So this is going to be another question that you're going to need to answer for the Easter egg hunt. All right. So they want us to look at sig figs for each of these items here. So we just basically need to look at the items here and count how many sig figs and write down just the numbers. So the first one, 45000 and then a dot. So that means all these zeros are significant here. So I have 5 sig figs. Okay. The next one, we have to count. So how many sig figs? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that would be 11 sig figs. Okay. The next one, this zero doesn't count. So 1, 2, 3 sig figs. And then some people say, well, how do you know if the zero in front counts or not? Usually, if you write the zero during the scientific notation, then it probably counts. If you don't write the zero, like the zero here, if you were to write this in scientific notation, you wouldn't write the zero, you write 4.56. So that means I know 4.56. These 3 numbers are significant. That zero is not significant. Okay. And then let's look at this one. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 sig figs. And then this one has 1, 2, 3, 4. 4 sig figs. Okay. All right. Let's go to the next question. This next question is going to require us to do a little bit of calculation with stoichiometry. And it says here, I have a chemical reaction N2O4 plus 2N2H4 equals to 3 nitrogen gas N2 and 4 H2O. And it says, if I have 33.58 grams of N2O4 and 61.23 grams of N2H4, can you find the maximum amount of N2 in grams that can be produced? So even though it says maximum amount on N2, it really means to look for the theoretical yield, which is the 100% yield. Now, when you do this question, we're going to take each of my reactants and then we're going to pick it to go to nitrogen, see how much nitrogen it can form. But One of them is going to be the excess reactant, one of them is the limiting. The excess reactant will look like it's going to make more N2, but it's impossible because once you hit the limiting, once the limiting reactant runs out, you can't make any more of the N2. So let's take a look. When you take 33.58 grams of N2O4, find out whether N2 is possible, how much of that, and then you compare that to 61.23 grams of N2H4 to how much product, how many grams, and then you actually pick the smaller number as your answer, even though it says maximum, because the maximum is really just the smallest number because it's the limiting factor, okay? So let's take a look at how we would do this. Again, we just want to put the numerical answer. Don't use scientific notation. No need for units as well. You do want to make sure you keep the correct number of sig figs. If you think about it, I have 4 sig figs here and 4 sig figs. Your answer is probably going to be in 4 sig figs. As you can see, all the numbers here are 4 sig figs. So the first one, we're going to take the first reactant, 33.58 grams of N2O4. And then we're going to find how much N2 you can make. And then the second line, I'm going to do 61.23 grams of N2H4. Now, in this case here, again, we always want to make sure we convert to moles. So 1 mole of N2O4, it's given here, is 92.02 grams. So I just converted the grams to moles. Then I do the mole to mole ratio, 1 mole of N2O4 to 3 moles of N2. And then from the 3 moles of N2, I get the moles of N2. I really want to convert it to grams. So it would be 1 mole of N2 is going to weigh 28.02 grams. That should give me my option for one of my nitrogens. I'm going to set the same thing up for N2H4 on the bottom, which you would do 1 mole of N2H4 is going to be 32.05 grams of N2H4. And then mole to mole ratio, 2 moles of N2H4. How do I know that? I looked at this equation. 2 N2H4 is 3 moles of N2. Again, I pick N2 on the top because I'm trying to cancel off the N2H4. I'm trying to get to go to nitrogen. And then we're going to do the same thing. We'll take the moles on the bottom and grams on the top using the molar mass to get to the grams of nitrogen as our answer. So if you put this together, you take 33.58 divided by 92.09 times 3 times 28.02. You should get your answer of, let's see, 30.675 grams of N2. Now I'm going to keep 4 sig figs, so I'll round that up. I'll underline 7. If I had to pick this answer, I'll write 30.68. But I don't know if this is the answer yet. I need to do my second one. So my second answer is 61.23 grams divided by 32.05 times 3 divided by 2 times 28.02. And you will get 80.296 grams. Now, obviously, 80 looks like a bigger number, but it's going to be impossible to make because once you make 30.675 grams of N2, you run out of this reactant. You don't have any more to keep going to make this much. So that means N2H4 is the excess reactant, N2O4 is the limiting reactant, and 30.68 is the correct answer for the theoretical view. All right, let's take a look at the next question. For the next question here, I wanted to show you the card. This is an UNO card, and it's 8 blue. This is going to be used in one of your treasure hunts or your Easter eggs. All right, so we have Al2S3 plus 6 waters. You make 2 AlOH3, and then you have 3H2S. That's the reaction is balanced. And it says you have this much Al2S3, this much water. So these are two reactants. And it says, what mass of Al2S3 remains unreacted? So they're saying there's going to be extra of Al2S3. Okay, it remains unreacted. So that's kind of nice. They gave us a hint of who is excess. Agree? Because it says what mass of this remains unreacted. So right away, if you caught that, you'll know Al2S3 is excess reactant, and this is the limiting reactant. So you know all of 12.49 grams of water has been used up. So if you know 12.49 grams of water has been used up, why don't we find out how much of Al2S3 is used up if you pair it with water? So to do that, you just need the molar ratio from water to Al2S3, which we have from the reaction is 6:1, and then you also have the molar masses. So we'll convert to moles first. 1 mole of water is 18.02 grams. And then once you have moles of water, we do mole to mole ratio. 6 moles of water used is really going to be the same as 1 mole of Al2S3 used. And then because I know how much of that in moles is used, let's convert it to grams, where I know 1 mole of Al2S3 weighs 150.17 grams. Now remember, this is how much was used. So the answer is how much was used. Okay? So if you know how much it was used and you know how much you started with, can you just get what's left over? So in this case, you would just say, okay, I'm going to get the answer here. Let's find out how much was used. And turns out you use 17. I'm going to write down extra numbers so you can see. 3.34 76 grams of Al2S3 use. Now really, how many Sigfigs do we want to keep? 4. This is unlimited. This is 5. So we really keep 4. So you would stop at 17.35 used. Okay. If you know how much was used, then you go, okay, 42.96 grams of how much we started off. And then we're going to use up 17.35 grams. That means my leftover is 25.61 grams. And this will be my answer. When I put down the answer, all right, just type in 25.6. And that would be my answer. All right. Let's go to the next question. On the next question, it says here, I have FeS2 reacts with oxygen gas, and they gave you the amounts in grams, and it says it makes Fe2O3 and SO2, and then how many grams of Fe2O3 are produced? So they're saying, I have a reaction of FeS2 plus oxygen gas, which is O2, goes to Fe2O3 and SO2. How much of the Fe2O3 are produced? So if they gave you 2 reactants, that means they're asking you for the theoretical yield of Fe2O3. Okay, it says you will need to balance chemical reaction before calculating your answer. Please type in your numerical answer with the correct Sigfigs without units. Don't use scientific notation. So number 1 is you're going to need your balanced chemical equation. So how are we going to do this? I'll write down FeS2 plus O2. And then we're going to go to Fe2O3 plus SO2. So those are my reactants and products. Now we're going to start balancing it out. So how would you start? Now, we would always leave, like in this case, the simplest one for last, because O2 is the simplest. We're just going to leave this one alone for last. And we can start maybe with iron, and we can do sulfur to make sure those are balanced, and then we count how many oxygens we need, okay? So if I wanted to do iron, I would say, well, I have 1 and I have 2, so by default, I know I need 2 here at least. Okay, now in this case here, then I'm going to say, well, I got my iron balanced, Let's look at my sulfur. Sulfur, I have 4 here, and I only have 1, so what I would like to do is put a 4 here. Now, the last step is we're going to count how many oxygen we have. In this case, I have 3, and then I have 4 times 2, which is 8. So 8 plus 3 will give me 11, correct? And it's like, well, I need 11 oxygen. How am I going to get O2 here to go to 11? We do our trick. We divide by 2. So, and then in this case, because it's divided by 2, we take the whole line times 2, and you really get the answer of 4 FeS2 plus 11 O2 goes to 2 Fe2O3 plus 8 SO2. That would be the balance equation. Okay, once you have it balanced, we can continue with our calculations. So they gave you the amounts of 2 reactants. So the first one, it says there's 327.2 grams of FeS2. And then the question also says you have 135.6 grams of oxygen gas. They're saying, how much of this can you make? Okay, I have the molar masses of everybody involved, so that makes my math a little easier. I'm going to start with the first reactant, set up to find out how many grams of Fe2O3. And we'll start with the second reactant, do the same thing, find out how many grams of Fe2O3. Now, if I want to find the theoretical yield, I will pick the smaller number. Remember, because once you run out of the small stuff, the small amount, once you make that, you run out of supplies to keep making more because there's a limiting reactant there. So let's try it out. First one, 327.2 grams, FeS2. I'm going to convert mole to mole ratio. So 1 mole FeS2 right there is 119.98 grams. Okay. Mole ratio, my mole ratio was 4 to 2 of my products. So 4 moles of FeS2 to 2 moles of Fe2O3. Why I put Fe2O3 on top is because I know I'm trying to cancel off the FeS2 to get to Fe2O3. Once I do that, I really need to cancel out the moles, and I really need to get my answer in grams of Fe2O3. That means I'm going to use the molar mass here. 1 mole of Fe2O3 is going to weigh 159.69 grams. Now, if you put this in your calculator, you should get your answer in grams of Fe2O3, but don't pick the answer yet because we need to do the second reactant still. Okay, so on your calculator, you put 327.2 divided by 119.98 times 2 divided by 4 times 159.69. And you're going to get an answer of, in this case, this one is going to be 217.7 grams. Now remember, don't just circle this one. Don't just put this answer as your answer because you still need to check the other in a reactant. So the other one is 135.6 grams of O2. Again, I'm going to turn it to moles, do a mole to mole ratio. 1 mole of O2 weighs 32.00 grams. Okay. And then for moles of O2, I have 11, and it goes to 2 moles of my product. All right. And now we use the molar mass. All right. If you put 1 mole on the bottom of Fe2O3, and the top is 159.69 grams of Fe2O3, you should get your answer in Fe2O3 in grams. So you would take on your calculator 135.6 divided by 32 times 2, divide by 11 times 159.69, and you would get your answer as 123.0 grams of Fe2O. Now, comparing these two options here, my answer of theoretical yield is going to be 123.0 grams. That's because once I run out of oxygen, I can't really make more than 123 grams of my product because I don't have enough oxygen to keep going. Okay, so oxygen is limiting. In this case, FeS2 is going to be our excess. put the answer here. And then we can go to the next question. Now, on the next question, let's take a look. This is an experiment. We have CuCl2 plus Al, 2Al. So 3 CuCl2 plus 2Al equals to 3 Cu plus 2AlCl3. And it says, if I have 51.19 grams of CuCl2 reacted with 16.72 grams of aluminum to produce 14.79 grams of copper, what is the percent yield of copper? So the question here is, what's the percent yield? Okay, so you have two reactants. You can find the theoretical yield, correct? Like the one we just did previously. You take these two reactants, turn it both to grams of copper. The smaller one is my theoretical yield of 100%. And then they say, well, when I did the experiment, I actually got 14.79 grams of copper. What is the percent yield? So you take the 14.79 divided by the theoretical yield, you would get the percent yield. And it says, type your answer in the correct sig figs without units. Don't use scientific notation. So same thing again, if you notice, the trend of stoichiometry usually starts with looking at your two reactants to figure out what your theoretical yield is and who the excess and who the limiting reactant is. And from there, a lot of stuff can be found. I'm going to start with 51.19 grams of CuCl2. And then I'm going to get it go to grams of copper. And then I'm going to do the same thing for the other reactant, 16.72 grams of Al. I'm going to turn to moles and then mole to mole ratio. And then we'll target towards grams of copper. So in this case here, 1 mole of CuCl2 is 134.45 grams. So in this case, I just use the molar mass, turn it to moles, and then I look at the equation. I have CuCl2, that's 3 moles, and then I will get 3 to copper. So it's 3 to 3. 3 moles of CuCl2 to 3 moles of Cu. Once I get moles of copper, I really want to get it to grams of copper, so I use 1 mole of Cu. It's going to weigh 63.55 grams. Now, this is found on the periodic table, but because it's already listed, we're just going to use it. It's faster. Okay, so that's 1, and then 16.72 grams of Al will do 1 mole of aluminum is going to weigh 26.98 grams. And then we'll do the mole to mole ratio. What's the mole to mole ratio? We have to look at the equation. 2 moles of aluminum to 3 moles of copper. So 2 moles of aluminum to cancel off. 3 moles of copper is what we want to get on the top. So we enter in moles of copper. 63.55 grams of copper is to 1 mole of copper. All right. Let's compare these two numbers. Remember, the smaller number is our theoretical yield, and we're going to use that to get our percent yield. So my first answer is going to give me 51.19 divided by 134.45 times 3 divided by 3 times 63.55. You get 24.19. I know the number keeps going, 57 grams. It keeps going, but we'll stop there. You don't really need that many numbers. You only need 4 sig figs. So it's 24.20, okay? And then, so all right, the next one, you put that in the calculator, 16.72 divided by 26.98 times 3 divided by 2 times 63.55, you will get 59.07 grams. And obviously this is the bigger one, so my smaller one is my theoretical yield. The bigger one is impossible because aluminum is excess. CuCl2 is my limiting reactant. So if this one is my theoretical yield, this is my 100% point. Okay, and they say, well, I really just made 14.79 grams of copper. So this is my actual yield. If you take actual yield divided by the theoretical yield times 100, you get the percent yield. So I would take 14.79 grams of Cu divided by 24. I can write the long number down. 1957. It keeps going. So we'll stop there. Grams of Cu times 100. You should get around 61.13%. And on your answer, you would just simply type 61.13 in your answer. I usually don't round this on my calculator. I let it keep going. So there's more numbers. 19579398. It just keeps going. I just didn't write all of it. You just take 14.79 divided by that long number, and then you times 100, you get 61.13%. All right. Let's go to the next question. The next question, it says, you have an unknown hydrocarbon compound. How many molecules of this unknown compound are found in 0.2284 liter of the sample? Assume the density of this hydrocarbon is 0.594 grams per milliliter and the molar mass is 58.43 grams per mole. Please express your answer in scientific notation. So scientific notation, if you have to type it out, example would be 1.234 and then star. And then you take 10 and you do the up sign, the symbol, and then whatever power it is that you need. +1, -1, -5, whatever it is. If it's negative, be sure to put the number in. All right, so let's try this calculation. It says, I need to find how many molecules. So you're gonna use the Avogadro's number, okay? And I have the volume in liters of the sample. If I have volume in liters, I can probably convert it to milliliters so I can use the density to connect milliliters and grams. Once I get grams, I'm going to use the molar mass to tie grams to moles. And once I have the moles, I can use the Avogadro's number to get the number of molecules. Okay, so remember, if I know 0.594, I'll write now 0.594, the density is grams. I'm just going to assume it's 0.594 grams is same as found in 1 milliliter. Then I can use this either on top or bottom to use whatever I need to use for my math to calculate. Same thing for molar mass here. I can just write down, well, 1 mole of this guy is going to be 58.43 grams. I just use the 1 on the bottom, basically, just assume it's 1. Okay? So those are my two conversions. I'm going to start. We have 0.2284 liters. Now I'm going to convert it to milliliters. So 1 liter is 1,000 milliliters. And then I'll cross liters, get my answer in mils, take mils, convert it to grams. So I'll put the grams on the top, mils on the bottom. 1 goes on the bottom. 0.594 goes on the top. Now I'm at grams. Now the next point is grams is to go to moles. So I'll write down, 1 mole is going to be 58.43 grams. So cross that one off. Now I have my answer in moles. Then you go, well, I also know that 1 mole contains 6.022 times 10 to the power 23 molecules. And that should give me my answer in molecules. So to put this in your calculator, you put 0.2284 times 1,000 times 0.594 divided by 58.43 times 6.022 times 10 to the power 23. And you should get an answer of like, how many sig figs do we need? We need 4 and 3, and then we have 4 and 4. So really, I'm keeping 3 sig figs. So even though my answer is 1.39887, blah, 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 it keeps going, times 10 to the power 24, I'm going to actually stop at my third number and write down that equals to 1.40. And then if I have to write times 10 to the power 24, I would just type the star sign, and then 10, and then up symbol, and then write down 24. That would give me the answer. Okay. And it says balance this chemical reaction. If it's one, write one in. I know usually we leave it blank if it's one, but in this case, if it's on the computer, go ahead and type the one in, even if it's a one. So let's take a look at how we do this. Remember, always keep the simplest for last. That means we do oxygen last because it's just one thing by itself, just oxygen. Okay, you do carbon and then hydrogen and then you do oxygen. So carbon, where are we going to start? Well, I see 3, now 1. So I guess by default, I would just say, well, I'm going to put 3 here. Agree? That's what I would do. Then I'll be like, okay, 3. And then, so if I have just 1 here and that's 3, that would balance on my carbon. Then let's count our hydrogens, okay? I have 7 plus 1, so I have 8 here. Agree? So if I have 8 hydrogens, I need 8 here. That's a H2, so I will need 4 of that. Do we agree? So I got my hydrogens balanced, got 8 hydrogens, and I got 3 carbons. The next thing I need to do is count how many oxygens I have. So that's 6 because it's 3 times 2. So 6 plus 4. Agree? So really I have 10 oxygen on one side. So then I need to remember, I make sure I have 10 over here too. There's 1 over here, right? Okay, forget that one. So really, if I already have 1, I really need 9 over 2 times O2 to get 9 plus 1 to go to 10. Now, because I have a half there, let's take this thing, it's 2. My real balance equation is 2 C3H7OH plus 9O2 goes to 6 CO2 plus 8 H2O. Always keep the simplest one, the element, for last. All right, let's try to do the next question here. We are at number 14, so I want to stop to show you this model here. This is a model of, I guess we can call this carbon dioxide because there's a carbon in the middle and 2 oxygen. This is how it would be bonded if it was double bonded. So you'll see later on, if you've learned Lewis dot structure in intro, you'll see that we have our molecules and this is what carbon dioxide looks like. All right, let's keep going. We're gonna solve this isotope question for number 14. It says an unknown element X has an atomic mass of, this is the average mass, 105.264 AMU. One of the isotopes has a mass of 108.411 and it takes up 29.4% abundance. Assuming there are only 2 isotopes, what is the atomic mass in AMU of the second isotope? Please report your answer with 3 decimal places without units. Don't use scientific notation. Okay, we can do that. All right, so let's set it up. The average is 105.264. That equals to the abundance of the first one times the mass of the first one. So 0.294 because it's percent turned to whole out of 1. And then 108.411. That's the first mass. And they're saying find the second AM. Right? So do you know the abundance of that one? If you know there's 2 of them, and they both make up 1. So if you take 1 minus 0.294, can you get the answer? So this is really 1 minus 0.294. And you'll see the answer here is 0.706. Right there. Okay. Then you want to solve for that AMU. Use your calculator. The way I would solve it is I would take 105.264, I would minus the product of these. And then I would take and divide by 0.76. Okay, so mathematically, this is algebra. I would take 105.264, and then I will minus the product of these 2. And then I would divide by 0.706. And that should give me my answer for the missing piece here. And I'm going to report 3 decimal places. So 103.953. All right. Next question. If I have a student that performs an experiment and gets a result for density of 1.09, 1.81, 1.93, and 2.73, and the actual number is 1.70, is this precise? Um, Precise means it's not all over the place, like it's all clumped together really closely. This is not clumped closely at all. So this is not precise. Okay. Is it accurate? Well, if you average them out and a number comes either really, really close to 1.7 or is that 1.7, um, then it will be accurate. If it's not, if it's a little far off, then it's actually not accurate. So if you take the add up 1.09 plus 1.81 plus 1.93 plus 2.73, and you divide it by 1, 2, 3, 4, and you get the average of 1.89. So 1.89 compared to 1.7 is actually far off. So we would say, nope, not accurate either. So in this question, you actually need to understand accurate means you get your answer like close, correct, to the real answer. And then precise means your answers must be grouped together really tightly. Okay, intensive versus extensive property. Intensive property is where the more of the stuff, the amount of stuff you have doesn't change the property. Okay, extensive is the more you have, the it varies with the amount. So the more water you have, the heavier the mass will be. Correct? So that would be extensive. So in this case, what mass is extensive? Okay. And then you say, well, the more of the water I have, does it change the density? No, water density stays the same depending on small amount of water, big amount of water. Water is water density. Water does not change. So this is intensive. If I have a bigger thing, more of the water or more of a block, wouldn't the width be bigger? Yes. So this is extensive. If I have more of it, do I change the viscosity? No, it doesn't. It doesn't matter. So viscosity is intensive. If I have more water versus a little bit of water, would the boiling point change? No, the boiling point stays as long as the environment stays the same. So this one is also an intensive property. So to recap, density is intensive, width is extensive, viscosity is intensive, mass is extensive, boiling point is intensive. So if you have like just properties here, you can definitely group, them all into each one. But if they say find the intensive, then you would just list 1, 2, 3 as your intensive. If they say find just the extensive, then you will list just the 2 extensive. So if they ask you for both categories, you give all the answers. If they ask for just the intensive, you need to select just the intensive ones and leave out the extensive. If they ask for just the extensive, then you just select the extensive, leave out the intensive from your selection. All right, next question. What is the empirical formula of a compound that is 52.1% carbon, 13.1% hydrogen, 34.7% oxygen by mass? So to do empirical formula, we say we take the mass, we take the percent and turn it to grams. Okay, and then from the grams, we go to moles, and then we do the mole ratio. So we need the molar masses of carbon, hydrogen, and oxygen. Now, obviously, you can look at the periodic table if you don't remember, but here's the periodic table that you see on a test. Carbon is given as 12.01, oxygen is 16, hydrogen is 1.008. So what I'm going to do is just going to write that down. I have 52.1 grams of carbon. I'll take the percent, turn it to grams. And then say 1 mole of carbon is 12.01 grams. And then I'll do the same, 13.1 grams, H, 1 mole of H, 1.008 grams of H. And then I'll do the same for oxygen, 34.7 grams of O, 1 mole of O is 216. Let's get the moles. So each one of them is giving just 3 sig figs. So my answer is gonna have 3 sig figs in the moles, but I'm gonna write extra down and just underline the correct where I stopped. So this is 4.338. So 4.33, so 4.34 technically. And then you will get for hydrogen, you will get 12.996. Obviously, we stopped the third one. And then 2.16875. So really, we keep the 3 sig figs here. I technically have carbon at 4.34, hydrogen at 13.0, oxygen at 2.17. Correct? I'm just rounding to 3 sig figs. Divide by the smallest number, which is 2.17. That's going to give me a ratio of C, this is 2, H is going to be 6, and O is going to be 1. So if I had to put an empirical formula, it would be C2H6O. Let's move on to the next question. Number 18. Combustion analysis of 0.150 grams of an unknown compound containing carbon, hydrogen, and oxygen. It's going to make you 0.2607 grams of CO2 and 0.418 grams of water. So these are my products. I know my reactant has C, H, and O, and you take that and combust it. You actually put oxygen gas to be lighted up and burn it, and then you'll make carbon dioxide and water. So combustion is always whatever you start with plus oxygen gas equals to CO2 and H2O. So they're asking you for the empirical formula of the compound of the unknown that has C, H, and O. So what you want to do is know that carbon dioxide is the source of carbon. All the carbon in that compound, because we're not adding any other carbon in there, is going to go to the CO2. All the hydrogen from the unknown compound is going to go into the water. But the oxygen is mixed. It's a mixed bag because it goes to CO2, it goes to water, plus you add oxygen from the reactant instead of just from the unknown compound. Because you have the unknown, write it up, plus O2, and then you make some amount of CO2 plus H2O. So the oxygen is really variable. So to do this, you would really need to find out if I have a total of 0.15 grams of unknown, right? How much of that is grams of carbon? How much of that is grams of hydrogen? Then I would get how much of that is going to get be oxygen, because this extra here is throwing things off. The oxygen count here is not going to be accurate. So what you want to do here is we are going to start with finding CO2 and get carbon. So we'll do 0.2607 grams of CO2. And then we're also going to do 0.418 grams of water. Okay. So from the CO2, I'm going to turn to moles of CO2. 1 mole of CO2 is 44.01 grams of CO2. Now, if you don't remember this, you can just look at the periodic table, because 12.01 and then 2 times 16 will add up to 44.01. And then you know that, okay, well, I got my moles of CO2, and every time I have 1 mole of CO2, I actually know that 1 mole of CO2 contains only 1 mole of C. So that should give me some amount of C, right? Whatever amount moles of C. Now, once I get the moles of C, I want to keep going, and I actually want to convert to grams of C. Okay, now my answer here is grams of C. Okay, so I have to stop at 2 answers. I'll do the moles for the empirical formula part, but I need the grams so I can subtract out C and then H from the 0.15 to get the grams of the oxygen in my unknown. So I'm just doing multiple steps. So I'm going to do the same setup for H2O, for hydrogen. 1 mole of H2O is 18.02 grams. Again, I just added up from the molar masses on the periodic table. And then you go, well, every time I have 1 mole of water, I really have 2 moles of H. Now I'm going to stop and get the answer for moles of H. And then I'll keep going and turn it into grams of H. So I'm going to try to cross up the units, moles to cancel out. Get the moles here, and then those to cancel out. You get grams, okay? Grams of water cancel out, moles of water cancel out, moles of H moles cancel off. You get grams of hydrogen. So we'll set that up. If you put in your calculator 0.2607 divided by 44.01, this is 1-to-1, so I don't have to add that. You should get the moles of carbon. And the moles of carbon is really small, so I'll write it down. It's 5.92 times 10 to the minus 3. Okay? Small number. And then you keep going on your calculator, what that number is, and you times 12.01, you should get grams of carbon. 0.07114. All right. And then that's 4. This was so 592. I'm gonna check to see what the fourth number was. 59236. 59236. I'll write it up here. And I really keep 4 numbers here. And then you have 4 numbers there. Anyway, let's keep going here. The next one, if you get the moles of H, you would get 0.01573. And then the grams would be 1586 grams. 0.01586 grams. And then we have the moles here. So for my unknown ratio, I have C is 5.923604 times 10 to the minus 3, and then H is 0.01573. Then I don't know what O is, right? I still don't know what O is. But I know grams of O now because I know it's 0.150 grams of the total minus 0.7 0.07114 grams C minus 0.01586. The number really keeps going. Grams of H. That's going to give me whatever grams of. So the grams of oxygen, really, you just keep 3 decimals, even though these have a ton of decimals. You're only going to keep 4 sig fix, but this one has 6. This one has 5 decimal, this one has 5. So you really want to keep 3. So the 3 decimal place answer for this one is 0.0. I'll write down 6299, but really you stop at 63. So you take 0.063 grams of O. We do the same thing here. See? 1 mole of O is to 1600 grams of O. That should give me moles of O. Let's see what the number is. Oh, we should leave more space. The moles of oxygen is going to be 3.937 times 10 to the minus 3. Really, I'm down to like 2 suffix. So it's 3.957. So really 3.3, 3.93. Yeah, it's 3.5. So you round to 3.9. All right, now 3.9 times 10 to the minus 3. So that's the smallest number. So everybody will divide by the smallest number. 3.9 times 10 to the minus 3 divided by 3.9 times 10 to the minus 3 divided by 3.9 times 10 to the minus 3. And you'll see this one, obviously O is 1. Hydrogen is, you're going to get 4. And then carbon, you're going to get 1.5. And you're like, still decimal. So what do you do to get rid of the 1.5? You times 2 for the everybody. And you get C3H8O2. That's your answer. And that's how you would get an imperial formula for a combustion sample. All right, let's go to number 19. Number 19 is going to talk about formula as well, but this one is molecular formula. To do molecular formula, you need to find the empirical formula first. In this case, it's given, and you need to have the molar mass. So before we solve this problem, I'm going to show you this cool model here. This is the model shape for a seesaw. So I want to show you here a model. You'll learn this later, but I want to show you why this is called a seesaw. When they say seesaw, this green cloud is invisible. Then you take a look. If the bottom here is the grass, right? And then you put a kid over here, and then you put a kid over here, and then you have the seesaw. So this is the model seesaw. Okay, you'll learn this at the end of the semester. It's really cool. Just wanted to show you guys that. All right, let's finish off number 19. So if I have the molar mass 92, let's find out what the empirical mass is. If NO2, let's find out N is 14.01 plus 2 over 16. What's my mass? It would be 46.01. That's the mass of the empirical formula. If you take the molar mass divided by an empirical mass, you take 92 divided by 46.01, you get the ratio of 2. This is the factor that you multiply the empirical formula to get the answer. So NO2 times 2 will give me the molecular formula. In this case, is N2O4. So it's simple once you know the empirical formula. Now, if they didn't give you the empirical formula, you might have to do the long way of the 2 previous questions to get the empirical formula first, and then do the division, and then to get the molecular formula. So you would have to look at question number 17 to do an example of empirical formula. Or you can also take a look at question number 18, which is a combustion empirical formula. So these are all related. Okay? All right. The chemical formula for magnesium nitride is, so this is a naming question. Magnesium doesn't need a Roman numeral because it's on the fixed charge list. Nitride, IDE, means it's a normal non-polyatomic ion, so just monoatomic ion from nitrogen. And nitrogen is in group 5 right here. And how many away from perfection is it? It's 1, 2, 3 away from perfection. So if N had to be a charge, it would be 3 negative. And then your magnesium, if you take a look, magnesium is in group 2, right there. So it would be 2 away from perfection of neon. So it would be 2 plus charge. So if you put Mg 2 plus and N3, they say crisscross, right? So really when you mean crisscross, you need 2 plus and another 2 plus. So there's like 3 of these and 2 of these to make it even. Okay, so the formula would be Mg 3 and 2. All right, let's go to the next question. The next question we have, it says, which one has the same number of electrons? Well, same number of electrons, we would need to look at, where they are in a periodic table. So let's look at the periodic table real quick. And it says O, O2 minus, and O2 plus. Well, these all have different electrons because this one, if it's neutral, it's 8 protons, 8 electrons. And then if it's a negative charge, you add electrons. If it's a positive charge, you take out electrons. So one actually has 8, and then the one has 10, and then one has 6. So that's not the same. What do they have the same of though? They have the same number of protons because it's oxygen, 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 and oxygen will always have 8 as the protons. So that's not the correct answer. And then you look at Sr2 plus. What does Sr2 plus look like? Strontium 2 plus. Strontium 2 plus is number 38. If you lose, you will get to 36 electrons. Okay, so one has 36. Ba2 plus is 56 minus 2 will be 54. Not the same. And then this one, radon, and then you have 88. And then you minus 2. So everyone's different. Not true. So that's not the same proton, not the same electron. They're all different. What's the same is they're all in the same group 2. Okay, let's look at carbon. Carbon has is neutral, so it'll be 6 protons, 6 electrons. And then nitrogen, in this case would be 3 negative, so 7 plus 3, it will have 10 electrons. This has 6, this has 10. Oxygen, 8 plus 2, also has 10. So this is 10, 10, and this one is 6. So not the same. These two are the same, but not carbon. Let's look at F negative. Plus 1, so 10. Neon also has 10. Magnesium also has 10. Okay? Because it's 12 minus 2. So the correct answer is D here. All right, let's take a look at this last question, number 22 here. It says element X has an atomic number of 19. So that means it has 19. The atomic number is the same thing as protons. So technically, if this is hypothetical, you technically could still look and say, oh, what's number 19? Number 19 is potassium. They really are talking potassium. X is potassium. But this is a hypothetical question. So it says here, its common ion is X plus, which has how many electrons? Well, if it's 19, has 19 protons, and if it's lost 1 electron to get X plus, it would have 18 electrons. Agree? And it will have 19 protons. Okay, so we get that part down. And then once you know that, it says the next question, if an isotope of potassium has a mass number of 41, and it says here, it contains how many neutrons? So how would you know the neutrons if it gave you the mass number? Well, you have to take the mass number is the total of protons and neutrons. So if you know your protons is 19, and you know protons plus neutrons is 41, you'll take 41 minus 19, and you'll get 22 as the number of neutrons. Okay, and it says the neutral atom of this isotope, which is in this case, we looked it up, it was potassium. It has how many electrons? If it's neutral, it would have 19 protons and 19 electrons. When it forms the X plus ion, its mass number does not change. It stays the same. What changes is the electron count changes. Okay, so if you had to write numbers in here, remember to put in just whole numbers. Don't use fancy numeric decimals or anything like that. Just whole numbers in there. And then you will pick out of these 3 options. In this case, it would be stay the same. And that's all we have for our review.